code, there are 4 basic time complexities that we can find. In order fastest to slowest, these are O of 1, O of log n, O of n, and O of n squared. To better understand these, we'll go over some examples. O of 1 is basically just searching a list from one number to another number that are known. You know exactly how long this is, and therefore we know exactly how long it'll take. O of n is the same thing, except we're searching all the way to a number that is unknown and can expand linearly as n grows. O of n squared is basically just searching from 1 to n inside of a list of 1 to n, so it comes out to n squared. Log n is a little bit more advanced. Just for time purposes, we're going to say it's sort of like searching from 1 to half of n in the worst case. This can be found in things like binary search trees. It'll become easier to spot once you see concrete examples that we'll go over. Before we start working through examples, we need to know that a simple operation on a line will always have a time complexity of O of 1, unless of course it's calling another function. So for example, if we had a is equal to the function getNumber, the time complexity of this line will be equal to the time complexity of the function getNumber. Here we have a simple loop that sets I is equal to 0, and as long as I is less than 5, adds 1 to I. Inside the loop, there's a simple operation that adds 10 to A each time the loop is run. I think the best way to analyze the code is to start from the outside and work in. So looking at the for loop, we know that I will be equal to 0, then 1, then 2, then 3, then 4. This is a list from 0 to 4, in which the ending number will never change. So we can say this is O of 1. We also have to analyze the inside of the loop, where A is always adding 10. And we know this is O of 1 as well. So the total function will be O of 1. If we take the for loop from our last example and switch out the number 5 with a number that we don't know, such as n, this will change the time complexity to O of n. A more practical use of this would be, let's say the user inputs their name. Let's say they input Bob. And we want to go through their name letter by letter. So we'd have I is less than name.length. We don't know what their name is. They could have inputted Bob, or they could have inputted a name which is 100 characters long. This would be O of n, because we can never be sure, and the time it takes to run this for loop will increase linearly with the length of their name. Spawning a function with log time is very simple. As we can see here, we have an O of n for loop. This counts from 1 all the way to n by 1. So it'll go 1, 2, 3, 4, 5, 6, all the way to n. A function with logarithmic time will, instead of adding by 1, it'll multiply I by 2. So this instead will count from 1, 2, 4, 8, all the way to whatever n is. As you can see, this is a lot faster than counting by 1 to n, so the runtime will be a lot faster than O of n. If we were, let's say, counting down, this would be done by the opposite of multiplying, which is dividing. So we'd start at I is equal to n. As long as I is greater than, we could say 0, depending on what you want to do with the function, it'll divide by 2. So as you can see, this is a lot faster than O of n. Here we have 2 a little bit more difficult examples. We're going to analyze the function do something first. So we have the for loop I is equal to 0, I is less than n, I times equals 2. So we know that this part is O of log n, as we went over before. The inner loop is going to be O of n, because it's just a list from 0 to n. And the inside here is just adding b to a. So this is O of 1. Then this for loop here is O of n. So what do we do when we're trying to find the complexity of the whole entire function? Well, we know that this O of n is inside of log n. So this whole part here can be simplified down to O of log n times n, which can also be said as O of n log n. And since these two are separate, we're adding the two together. So that simplifies down to n log n plus n. And we're going to take, when stating the whole time complexity, all we do is simplify down to whatever the greatest or the slowest part is. So it'll be n log n for the whole function. For do something 2, it's similar. We have I is equal to 0, I is less than n. So we know this is O of n. The inner part is from 0 to 10. So this is just O of 1 here on the inside. So O of n times O of 1. We just take the slowest part, which is O of n. So this whole function will be O of n.